Welcome to Hybridization and the Localized Electron bonding model. So let's consider the methane molecule, which looks a little like this, although you should know after the last video that the actual three-dimensional structure doesn't look like that. But in general, we assume that chemical bonding only involves the valence orbitals. This means that the 1s orbital for hydrogen and the 2s and 2p orbitals for carbon are what we are interested in looking at here. So the localized electron model assumes that the electrons occupy the atomic orbitals. This causes two problems for methane. One is that using the 2p and 2s orbitals for carbon will lead to two different types of carbon-hydrogen bonds, because we have the 1s orbital from hydrogen being involved with the 2s or the 2p for carbon, which means that we should have two different types of carbon-hydrogen bonds, one where we have 2s from the carbon and 1s from the hydrogen, or one where we have 2p from the carbon and 1s from the hydrogen. But we don't see that. We only see one type of chemical bond. Furthermore, the carbon 2p orbitals must be mutually perpendicular. They're all aligned along one of the three axes. So that means that 3 out of our 4 carbon-hydrogen bonds must be mutually perpendicular. We must have 90-degree angles between them. But we know from the last video that the molecular structure and the electronic geometry in methane is tetrahedral, in which those bond angles are 109.5 degrees. They're not 90 degrees. And so there's something strange going on here. It can't be that we're using these atomic orbitals to create our bonds. We have to be doing something else. And so, again, using our 2p and 2s orbitals will give us two different bond types. Again, one where we have a 2s of the carbon involved with the hydrogen, and one we have, and 3 where we have the 2p involved with the carbon. But we have 4 identical bonds. Okay? So there's one of our problems. And the other is where we have this sort of structure. This is what we really see in methane. But the p orbitals are 90 degrees apart. Now, one of these hydrogens should be sticking out of the board, but 3 of them should still be mutually 90 degrees apart, and we don't see that. We see this 109.5 degree angle. So our model has to be wrong, and we need to fix it. We need to patch our model in some way, or maybe come up with a new model. So we need to get rid of the localized electron bonding model because it's not working for us. We need to come up with a hybrid model, a hybridization-based model. So let's fix our model by assuming not that the atomic orbitals are occupied by the electrons, but that a new set of orbitals are occupied. So the localized electron bonding model is assuming that those electrons are occupying the orbitals that were in the atoms before they bonded. And now we're saying, no, we need to come up with some new orbitals. And these new orbitals are where these electrons are going to go. So in methane, we need 4 orbitals that are arranged in a tetrahedral geometry, so they have to be 109.5 degrees apart, around our carbon atom. So we can do this. We can obtain 4 such orbitals if we combine the 2s and 2p orbitals of our carbon atom together. So if we mix these orbitals together, this is called hybridization. We're creating a hybrid of 2p and 2s orbitals. And these new orbitals are called sp3 hybrid orbitals. So we say that the carbon atom undergoes sp3 hybridization to form these new orbitals used in our chemical bonds in methane, and thus our carbon atom is sp3 hybridized. So here we have our atomic orbitals. We have our 1 of our 2s orbitals. We have 3 of our 2p orbitals, one along each of our 3 axes. Now those are all 90, the 3p orbitals are 90 degrees apart from each other. If we hybridize these, so we combine together the s and the p orbitals, then we get 4 orbitals that look something like this. So they're 2-lobed, but one of the 2 lobes is substantially larger than the other one. And they're pointing in different directions. And the way that we combine these together gives us orbitals that are able to point in 4 different directions that are all 109.5 degrees apart. So when we add these together, if we sort of overlap them, we get a structure that looks like this. That's our tetrahedral geometry that we need for methane. So if we hybridize our orbitals together, now we can represent this hybridization, this mixing of our s and p orbitals on an energy diagram. So our 2s orbital starts off lower in energy than our 2p orbitals do, but when we mix them together, they end up at the same energy. So we hybridize them, they're all 4 of them at the same energy. Now these we've labeled sp3 because they're sp3 orbitals. They're no longer s or p orbitals. They're sp3 orbitals. Now you notice that here we have one 2s orbital that's lower in energy than the 2p's, and those 3p's are at the same energy. Well, when we hybridize them together, we end up with orbitals that all have exactly the same energy. But when we've mixed them, the 2p, the energy is lower than the 2p, but it's higher than the 2s. It ends up being the average of these 4 orbitals. The average of these 4 orbitals is the same as the average of those 4 orbitals. So overall, we're not changing the energy if all 4 of these orbitals and all 4 of those orbitals were occupied. So each of these new sp3 orbitals on the carbon atom is overlapped with a 1s orbital from a hydrogen atom, and that then creates a carbon-hydrogen bond. So now let's look at a molecule of ethene. With ethene, we have a double bond in there between the 2 carbon atoms. So here we have a trigonal planar geometry. We need to be able to get 3 bonds, so 3 orbitals, 120 degrees apart. So we need to be able to get a structure that looks something like this. But we can't do this with our sp3 hybrid orbitals. But we also can't do it with our atomic orbitals, because our atomic orbitals, again, are 90 degrees apart for the p orbitals. So we need to get a new hybridization. The sp3 hybrid orbitals don't work, our atomic orbitals don't work, so we need a new hybridization, the sp2 hybridization. So we can do this if we take the carbon's 2s orbital and 2 out of our 3 2p orbitals. We're going to leave our third 2p orbital unhybridized, and we'll create 3 sp2 hybrid orbitals. So now our sp2 hybrid orbitals are sort of these yellow ones that are all in the plane, and then we've got our 1 p orbital left over. Remember, the p orbital is 2-lobed, and so this is our p orbital that's left over. That one we can use for something else. We can fill it up with a lone pair, or we can use it for a different sort of bond. In this case, we're going to use it for a different bond. So an energy diagram looks something like this. Again, we start out with our 2s and 2p orbitals at various energies. When we hybridize, we're going to leave one of the 2p orbitals at exactly the same energy that it was before, but we're going to take 2 of the other ones and the 2s, mix them together, and we're going to get lower sp2 hybrid orbitals. And again, the average of those 3 orbitals is the same as the average of the 3 that we took from over there. So the carbon atoms then, each then use these sp2 hybrid orbitals to form a single bond with the 2 hydrogen atoms and the other carbon atom. So that's the 3 hybrid orbitals. So each of these bonds that's formed by overlapping atomic or hybrid orbitals is called a sigma bond. So we have a sigma bond here between this hydrogen and the carbon. We have a sigma bond here between the hydrogen and the carbon. Again, both of those involving the sp2 hybrid orbitals from the carbon and the 1s orbital from the hydrogen. We don't need to hybridize the orbital in hydrogen because we just need to form one bond. We can do that with the 1s. And then each carbon has this overlapping of an sp2 hybrid orbital with an sp2 from the other carbon, and so that's a sigma bond. So each carbon has 3 sigma bonds, one here, one there, one here, or for this carbon, one here, one there, one here. Now, the electrons in a sigma bond occupy the space directly between the 2 nuclei. So on a line between the 2 nuclei, a line that connects those 2 nuclei, that's where, or at least the average position of those electrons is. But remember that our 2 carbon atoms need to be able to share 4 electrons, 2 pairs. We need to be able to get a double bond in there. And we can't put more electrons directly in between. We can't get us another sigma bond in there. So each carbon atom still has that unhybridized 2p orbital. That's what we need to use. So these two 2p orbitals don't directly overlap, but if the 2p orbitals are parallel to each other, then the electrons can occupy the space above and below the sigma bond that's between the two carbon nuclei. So this sort of bond involving unhybridized p orbitals is called a pi bond. And so that looks something like this. Now we've removed the two hydrogens from each carbon, but you can see that here we have our carbon-carbon sigma bond here in yellow, and then this is that one unhybridized p orbital from one carbon, and here's the other unhybridized p orbital from the other carbon. And as long as these line up, now we can rotate around this bond, so we can get those two p orbitals to line up. That then there's sort of the region in here above that sigma bond, and the region down here below that sigma bond. Now we could orient it a different way in front of and behind is fine too. But those two regions can sort of overlap, and we can create another bond up here and down there between those two carbon atoms, and it still will act as a bond to pull those two carbon nuclei together. And so that is where that double bond is coming from. So a double bond now involves one sigma bond directly between the nuclei and one pi bond above and below that sigma bond. So what about a triple bond? Can we use sp3 hybridization? Can we use atomic orbitals? Can we use sp hybridization to do this? Pause the video and think about it. So let's look at a molecule of carbon dioxide. Carbon dioxide is linear, with the two oxygen atoms 180 degrees apart. So our Lewis structure looks something like this: carbon, double bonded oxygens. There are some lone pairs on the oxygens. The molecular structure looks like this. All three of those atoms are collinear. So we need to be able to get two regions of electron density 180 degrees apart. Well, none of our atomic orbitals, or our sp3 or our sp2 hybrid orbitals, have a linear geometry. Because remember, the sp3 hybrid orbitals have an angle between them of 109.5 degrees. The sp2 hybrid orbitals have an angle between them of 120 degrees. The atomic orbitals have an angle between them of 90 degrees, at least between the p orbitals too. And so we need to be able to get 180 degrees, linear geometry. We can't do that with any of those. So again, we need a new type of hybridization. We need sp hybridization. So we can hybridize the carbons 2s and 1 of the 2p orbitals, leaving the other two remaining 2p orbitals unhybridized. And this will now give us two new sp hybridized orbitals. So we take our s and we take one of our p orbitals, we mix them together, so we get two orbitals that look like this. Now those guys are 180 degrees apart, as we see there. And now we can get one oxygen atom bonded over here and one oxygen atom bonded over there. So the carbon atom forms one sigma bond with each oxygen atom, using one of our two sp hybrid orbitals. And then the carbon then has two other 2p orbitals remaining, which are each perpendicular to each other and to our sp hybrid orbitals. And so each oxygen atom has to be sp2 hybridized because they each have three regions of electron density surrounding the nucleus. They each have two lone pairs of electrons and two bonding pairs, but those two bonding pairs are both in between the oxygen and the carbon. So this leaves one 2p orbital for each oxygen unhybridized after we form these sp2 hybrid orbitals. And this means that the unhybridized p orbitals from oxygen and the unhybridized p orbitals from carbon can be used to form our two pi bonds. So note that because our two unhybridized p orbitals on the carbon are perpendicular to each other, the plane involving those pi bonds has to be at 90-degree angles to one another. They have to be perpendicular to each other. So we end up with something like this. So this oxygen has the p orbital, has its unhybridized p orbital coming out of the board, and that will then bond with a pi bond with the p orbital coming out of the board for the carbon, so that that's in a plane sort of this way. And then this oxygen has its p orbital in the plane of the board going up and down, and that will form a pi bond with the p orbital that's unhybridized in the carbon that's going up and down in the plane of the board. But that means that the plane of this pi bond, which is this way, and the plane of this pi bond, which is this way coming out of the board horizontal to my floor, those two planes are perpendicular to each other. And this means that now, in this molecule, we won't be able to rotate this oxygen with respect to that oxygen, because now they're both fixed in place. They have to be in that orientation around that carbon atom. So, now let's take a short aside here and talk about diatomic carbon. So we know that we have a lot of nonmetals that form diatomic molecules. But can we get diatomic carbon? Or rather, why is it not a diatomic molecule? So let's look at acetylene, which is C2H2. So we have a structure that looks something like this. We've got 4 bonds on each carbon. So 2 regions of electron density, one in between the 2 carbons and one outside between the carbon and the hydrogen that it's bonded to. Each carbon then has to be sp hybridized, which leaves 2 p orbitals unhybridized on each carbon atom. The 2 p orbitals are perpendicular to each other, and we can then use them to form 2 pi bonds between the 2 carbon atoms. So each carbon atom has a sigma bond with a hydrogen atom on the outside, here and there, and a sigma bond with the other carbon atom directly in between along the axis there. And then 2 pi bonds, one above and below, and one in front of and behind the axis connecting the 2 carbon atoms together. And so now we have a triple bond, and now we know that a triple bond is 1 sigma bond and 2 pi bonds, where a double bond was a sigma bond and 1 pi bond, and a single bond was just a sigma bond. So now let's look at a hypothetical C2 molecule, a diatomic carbon molecule. So each carbon atom has to form 4 bonds, so a quadruple bond. We have to get 1 region of electron density and 4 bonds in there. This quadruple bond has to be formed from 1 sigma bond and 3 pi bonds. We could form the sigma bond out of the 2s orbitals, atomic orbitals from carbon. That would give us a sigma bond. But now we need to be able to get 3 pi bonds. Now the pi bond requires a set of parallel p orbitals. But we can't get more than 2 to be lining up. Because however we orient it, our 3 p orbitals are mutually perpendicular to each other. So if we have 1 carbon atom here and the other carbon atom is there, it will have a set of orbitals going up, which can match with the y orbitals from this carbon. It'll have a pair of orbitals, a p orbital coming out and back, that will match with the z, but its x orbitals will directly overlap this px orbital from this carbon. And that means that we can't get them parallel, because they're going to be linear. We can't get them not along that same line, that same path in between the 2 carbon atoms, 2 carbon nuclei, as that sigma bond was. It has to be in a different region, a slightly different region, but it has to be in a different region. And so we can't get more than 2 sets of parallel p orbitals. So one atom can't ever have more than a triple bond, because it can't ever form more than 2 pi bonds. If it can't ever form more than 2 pi bonds, it can't make a quadruple bond, which would require 3 pi bonds. So we can't do it. We can't make a quadruple bond. We can have a single bond, double bond, or triple bond, but we can't have a quadruple bond with anything, which means that we can't make diatomic carbon. It can't be a diatomic element. So, we have 2 more hybridization types that we need to look at. So let's look at phosphorus pentachloride. We looked at this the structure of this molecule in the last video. So the phosphorus atom here has 5 regions of electron density around it. Again, neither the atomic orbitals nor any of our other hybrid orbitals have this trigonal bipyramidal geometry. So we need a new hybridization, one that involves 5 regions of electron density, which means 5 orbitals have to be hybridized, which means we need another orbital. We need a d orbital now. So we're going to take one of our d orbitals, our s orbital, and 3 of our p orbitals, and hybridize them into our trigonal bipyramidal arrangement. So, in phosphorus pentachloride, how many sigma and how many pi bonds are there? And what is the hybridization of each of the chlorine atoms in our phosphorus pentachloride? So now let's look at sulfur hexafluoride. So now we have our sulfur atom, we have 6 regions of electron density because we have 6 fluorine atoms bonded. Here we have, again, none of our previous hybridization types will work. We need to pick up another d orbital, so now we have d2sp3 hybridization. And I want to point out that there's a difference between d2sp3 and sp3d2, or dsp3 and sp3d hybridization. It matters whether you put the d in front or behind. So d2sp3 hybridization uses the n-1th d orbital and the nth s and p orbitals. So where n there is the period that the element is in. So for sulfur, sulfur is in period 3. So for sulfur, d2sp3 would use the second d orbital, so the 2d, and the 3s and 3p orbitals. Whereas sp3d2 hybridization uses the third sp and d orbitals, or the nth, whatever period the element is in. So for sulfur, again, that would be 3. So here, in this case, sulfur needs to be using the second d orbital, the 2d. There is no 2d orbital, which means sulfur can't do d2sp3 hybridization. Sulfur can't do this one. It has to do this one. It has to do the sp3d2. Now, the next period down can do d2sp3. So if you look below sulfur, anything in period 4 or below, those can do d2sp3 or dsp3 hybridization. So, again, which does sulfur hexafluoride use? Well, we know that it has to be sp3d2, because anything in the 3rd period or above can't do, anything in the 3rd period can't do d or d2sp3 hybridization, because there is no 2d orbital. Now, anything in the 1st or 2nd period can't even do the sp3d2 or sp3d, because there's no 2d, there's still no 2d around. So those atoms, so these guys in periods 1 and 2 can't ever have more than 8 valence electrons. They can't ever have this sort of octahedral geometry to them, or the trigonal bipyramidal. So only atoms down here in the 4th period can use the d2sp3 hybridization, or periods below that. So that was hybridization and the localized electron bonding.